Assalamualaikum, my name is Siti Rohaila and my metric number is 066242. Today, I want to tell you about ARM processor. The ARM microcontroller stands for Advanced RISC Machine and is one of the world's most widely used and licensed CPU cores. Cambridge University created the first ARM processor in 1978 and the Acorn Group of Computer created the first ARM RISC processor in 1985. The ARM architecture has been designed to allow very small yet high performance implementation. The architectural simplicity of ARM processors leads to very small implementations, and small implementations allow devices with very low power consumption. The ARM is a reduced instruction sets computer, RISC, as it incorporates these typical RISC architecture features, a large uniform register file, a store architecture where data processing operations only operate on register contents, not directly on memory contents. Simple addressing mode with all store address being determined from register contents and instruction fields only. Uniform and fixed length instruction fields to simplify instruction decode. In addition, the ARM architecture gives you control over both of arithmetic logic unit (ALU) and shifter in every data processing instruction to maximize the use of an ALU and a shifter. Auto increment and auto decrement addressing modes to optimize program loops. Load and store multiple instructions to maximize data throughput. Conditional execute of all instructions to maximize execution throughput. These enhancements to a basic RISC architecture allow ARM processors to achieve a good balance of high performance, low code size, low power consumption, and low silicon area.
Different ARM Cortex controllers exhibit particular scalability and performance features that are most suited to specific applications. These three highly useful processor types were designed to provide the needed support and cater to our applications' needs perfectly. The Cortex-A category of processors is dedicated to Linux and Android devices. Any devices starting from smartwatch and tablets and continuing with networking equipment can be supported by Cortex-A processors. Cortex-R processors usually target real-time solutions. They find application in controllers, networking equipment, media players, and other similar devices. This type of ARM processor provides great support for the automotive industry. The ARM processors of Cortex-M type find their implementation in FPGA, integrated memories, and clocks. Different members of the set have different improved features. Each of the designed controllers is tailored to a particular segment of the market.
Hi, Assalamualaikum warahmatullahi ta'ala wabarakatuh. My name is Muhammad Farhan bin Muhammad Zaini. My matric number is 067C33. The ARM940T has a 4KB instruction cache, a 4KB data cache, and an 8-word write buffer. The instruction cache and data cache has similar architecture. Each cache is made up of 4 fully associative 1KB segments that provide single cycle reads and 1 or 2 cycle writes, depending on the access sequentially. The mesh line is enabled and the data can be accessed if a mesh or a head happens. If none of the text mesh, a missed external memory must be accessed unless it is a buffer write, in which case the write buffer will be.
Assalamualaikum, my name is Nur Fazanali Nabidikar Anwar. For my part, I will discuss the advantage and disadvantage of ARM. First advantage of ARM is because it does not require expensive equipment. The ARM is relatively economical to manufacture. It costs a lot less than other CPUs. As a result, they're great for low-cost phone and other electronic gadgets. Secondly, ARM processors use less energy. They were created with the intention of using less energy. They even use less transistors in their design. They have a variety of other threads that make this possible. Next, it works faster since they only perform one operation at a time. Facilitate the procedure. It reads quicker since it has a lower latency. RAM also have a longer battery life. When administering device with and without ARM CPUs, this is visible. Those who use ARM processor work longer hours and were released later than those who did not. Store and load store architecture is used in the CPUs, which store label in several registers. It contains separate load and store instruction for sending data from external memory to the register bank. The basic of circuit. ARM processors are extremely tiny and may be used in small devices. They comprise fundamental circuit. ARM also support both virtual address translation and memory protection. The disadvantage is that it cannot be used with Windows since it is incompatible with x86, and some CPUs have speed limit that might cause problem. It also including instruction also might be difficult with ARM processor. Finally, the programmer instruction must be followed to the letter. This is because the execution ARM processor determine their overall performance.
Hi, hello everyone. My name is Monica Matthews, metric number 065353. Today I would like to tell about characteristic of ARM processors. ARM processors are developed to serve the needs of three system categories according to the ARM website, which is arm.com. Embedded real-time systems in all of them, and it is a system for storage, industrial, automotive body and powertrain, and networking application. Secure software for smart card, SIM card, and payment terminals are also available. Aside from that, there are application platforms in a wireless consumer entertainment and digital photography for device running open operating systems such as Linux, Symbian OS, Plum OS, and Windows CE. Thank you.
Assalamualaikum and hi, my name is Syamil Hakimi bin Syamsul Bahrain, matrix number 066862, and I'll be explaining about ARM memory management with the subtopic of memory system organization and virtual memory address translation. So let's begin with memory system organization. In order for a program to be executed, the processor and the memory needs to communicate, and the processor and the memory communicate using cache, and ARM, the processor, will provide the virtual address. The MMU will translate it. MMU stands for Memory Management Unit, and then the MMU will translate the address into physical address and give it to the main memory for it to be executed. So in MMU, there's something called TLB, that stands for Translation Local Site Buffer. TLB is a cache of recent page table entries. So there's a few cases for when ARM or processors giving out virtual addresses and the route. So I'll be explaining for each example. So the first example is when the entry is already in TLB. So when the entry is already in TLB, TLB will directly send the physical address to the main memory so it can be executed or be read. The next example is when a logical cache organization is used. Logical cache organization is a set of system functions that allow an application to define and use memory cache. So when this happens, the ARM will supply the virtual address directly to the cache, and as well as supplying it also to TLB when the cache miss occurs. And then it will be sent to the main memory. The next one is when a physical cache organization is being used. Physical cache organization is when storing data using main memory physical address. So when a physical cache organization is being used, TLB must supply the physical address to the cache, and then the cache will give it to the main memory. Alright, the next one is the virtual memory address translation. So when a program is being executed, it will send a virtual address for it to be sent to the main memory. But as I said before, it will be needed to change the physical memory in order for the main memory to be executed. So when the virtual address is provided by a program, the processor will divide it into a few sections, and usually the back section of it in this picture is the page offset. So the page offset will remain the same even in the virtual address or in the physical address. It will remain the same. The page offset tells us where in the page we are, and then in front of the virtual address there is a virtual page. So in this example, in the picture, it shows that the virtual address is FC519085. So the blue part, the FC519008B. So the page offset for this virtual address is 08B. And the virtual page is FC519. So the FC519 and then will be brought to the page table and then will be inserted into a framework. So the framework for this example, the FC519 is being put into 00152. So now the virtual page has become a physical frame. In order to complete the physical address, the physical frame needs to be combined into the page offset. As I said before, page offset doesn't change even though it is in virtual address or in the physical address. So in this case, the physical frame is 00152, and then the page offset is 08B. So when it's combined, the physical address is 00152, 08B. And
to get a better understanding of the ARM memory management, we consider the key formats as shown in figure 8.24. The control bits shown in this figure are defined in table 8.6. For the level 1 table, each entry is a descriptor of how its associated 1 MB virtual address range is mapped. Each entry has one of 4 alternative formats. Bits 1 to 0 equal to 00. The associated virtual address are unmapped, and attempts to access them generate a translation fault. Bits 1 to 0 equal to 01. The entry gives the physical address of n level 2 page table, which specify how the associated virtual address range is mapped. Bits 1 to 0 equal to 01 and bit 19 equal to 0. The entry is a section descriptor for its associated virtual addresses. bits 1 to 0 equal to 01 and bit 19 equal to 1. The entry is a supersection descriptor for its associated virtual addresses. Entries with bits 1 to 0 equal to 11 are reserved. For memory structure into pages, a two-level page table access is required. Bit 31 to 10 of the level 1 page entry contain a pointer to a level 1 page table for small pages. The level 2 entry contains a 20-bit pointer to the base address of a 4 KB page in main memory. For large pages, the structure is more complex, as with virtual addresses for small pages. A virtual address for a large page structure includes a 12-bit index into the level 1 table and an 8-bit index into the level 2 table. For the 64 KB large pages, the page index portion of the virtual addresses must be 16 bits to accommodate all of the level 2 table index field. ARM accommodates this overlap by requiring that each page table entry in a level 2 page table that supports large pages be replicated 16 times. In effect, the size of the level 2 page table is reduced from 256 entries to 16 entries. If all of the entries refers to large pages, however, a given level 2 page can be serviced a mixture of large and small pages. Hence, the need for the replication for large pages entries. For memory structure into section or supersection, a one-level page table access is required. For section, bits 31 to 20 of the level 1 entry contain a 12-bit pointer to the base of the 1 MB section in main memory. For supersection, bits 31 to 24 of the level 1 entry contain an 8-bit pointer to the base of the 16 MB section in main memory. As with large pages, a page table entry replication is required. In the case of supersection, the level 1 table index portion of the virtual address overlaps by 4 bits with the supersection index portion of the virtual address. Therefore, 16 identical level 1 page table entries are required. The range of physical address space can be expanded by up to 8 additional address bits 23 to 20 and bits 8 to 5. The number of additional bits is implementation dependent. These additional bits can be interpreted as extending the size of physical memory by as much as factor of 2 to the power of 8 equal to 256. Thus, physical memory may in fact be as much as in 256 times as large as the memory space available to each individual process. The API access controls bit in each table entry govern a given process access to a region of memory. A memory region can be marked as no access, read only, or read write. Furthermore, the region can be designated as privileged access only, meaning it can only be used by the operating system and not by application. ARM also makes use of the concept of a domain, which is a collection of sections or pages with specific access permission. The ARM architecture supports a total of 16 domains. The domain feature enable multiple processes to use the same translation tables while remaining somewhat isolated from one another. Each page table entry and TLB entry has a field that indicates which domain the entry belongs to. Each domain access is controlled by a 2-bit field in the domain access control register. Each field enables and disables access to an entire domain quickly, allowing entire memory areas to be swept in and out of virtual memory very efficiently. There are 2 types of domain access supported. First is client, user of domain who must adhere to the access permission of the domain's individual section or pages. Second is manager, control the domain's behavior and bypass access permission for table entries in that domain. One program can be a client of some domains and a manager of others while having no access to the others. This enables extremely flexible memory protection for programs that access various memory resources.